Welcome back. In this video, we're going to be talking about correlation and regression. All right, we'll get started with correlation. Correlation is the strength and relationship between two variables. So you've often heard the word correlated in the real world, and you probably have a general idea of what it means. But now we're just going to apply a well-defined numerical value to correlation. So the values for correlation range from -1 to 1, where -1 and 1 are perfect relationships. And 0 is no relationship whatsoever. So the closer we get to -1 or 1 is a strong relationship, and then as the number gets closer and closer to 0, that's less and less of a relationship. So positive correlations, those that are close to 1, positive 1, are things where as one variable goes up, so does the other one. So an example is height and shoe size. So when you were a child, you were probably not very tall and you had a small shoe size. As you got bigger, you got taller and your shoe size got larger. So those things tend to go up about the same. Another positive correlation is temperature and swimwear sales. So in January, probably not a lot of swimwear sales going on, but as we get closer to summer, swimwear sales tend to pick up. So as one of those goes up, so does the other one. Some examples of negative correlations, that is, as one variable goes up, the other variable goes down. So those are correlations closer to -1. So for example, hours of exercise per week and blood pressure. So if you exercise regularly, you typically have lower blood pressure. It's not 100%, but often the more you exercise, the lower your blood pressure. And then temperature and snow shovel sales. So kind of the opposite of temperature and swimwear sales. In July, probably not a lot of people buying snow shovels. That's when the temperature is high. But as the temperature drops, as the temperature gets lower, the sales of snow shovels will increase. So those are negative correlations. So again, -1 is a perfect relationship just in the negative direction. +1 is a perfect direction or perfect relationship in the positive direction. All right, so let's look at a couple of correlations just to kind of get an idea. So correlations are often shown as a scatter plot. So a scatter plot is just an image with a bunch of points, data points, an x value and y value, or x-axis and y-axis, where each point has an x value and a y value. So the one I've drawn here, there's just kind of a blob of points. And so this would likely have a correlation, which is the letter R. It would likely have a correlation of 0. There does not appear to be any pattern. As x gets larger, y does not tend to get larger or tend to get smaller. There's just no pattern whatsoever. So that's 0. We could have, if we had a perfect relationship, so a perfect positive relationship, for example, that is, as x goes up, y goes up. So this would be a correlation of R equals 1. Every time x goes up, y goes up. Now, very few types of data have a perfect relationship. Typically, we see things that have a positive trend but aren't perfectly related like this. So let's look at a couple other examples. One of the problems with correlation is we can often have things like this, which this would have a correlation of 0. It's, again, just kind of a blob of points. But if we had an outlier, so an outlier is a point that does not fit the mold. This can make it look like there is a correlation. So maybe, and I'm making this up, this could have a correlation of maybe 0.4 because one point happened to pull it up. So when this sort of thing happens in the real world, when you have an outlier, it's important to know about those outliers and to be able to kind of dig deep into what they are. Often outliers are mistakes in the data. If you gave a survey, for example, an outlier could be someone accidentally typed something in wrong. And in that case, you could delete the outlier. Though if it's a real point, it becomes a little bit trickier. You'll probably find out more about that if you take a bunch of statistics classes. But anyway, so we do have to be careful of outliers. So one of the other things to be careful of with correlation is that correlation is only linear. So it can only measure linear relationships. So if we take the relationship between two variables, let's say height and age. So as people are younger, they are less tall, and as they get older, they tend to grow, right? But this eventually tapers off, right? You don't just keep growing forever. Eventually, your age keeps getting bigger or keeps getting larger, but your height does not. And so if we were try to measure something like this with correlation, it would not really be very accurate because it's not a linear relationship. It is up through, maybe your early teenage years, but past that, it's no longer a linear relationship. So correlation can only be used for linear data, at least the correlation R, which is the only one that we'll talk about in this class. All right. One of the other things to be careful of with correlation is that correlation does not mean, it doesn't equal causation. In other words, it does not say that one thing causes the other. A correlation indicates a relationship, but it does not say a change in X causes a change in Y. It says a change in X often occurs at the same time as a change in Y. So our example here is a scatter plot. There are also lines drawn between the points, but the y-axis is mozzarella cheese consumption per capita, and the x-axis is civil engineering doctorates awarded between the years 2000 and 2009. The correlation here is R equals 0.958648, so almost a perfect correlation between number of civil engineering doctorates awarded and the per capita consumption of mozzarella cheese. So, do we think that people eat more cheese because more civil engineering doctorates are awarded, or vice versa? And the answer is no. These things are completely unrelated. They just happen to be happening at the same time. So I'll give you a little hint. There's a homework question, at least one homework question, where it asks about a variable, which variable causes the other. And the answer is neither. One does not cause the other. A high or a correlation close to 1 or -1 indicates a strong relationship, but you need other things to be able to say this variable causes this other variable to go up or down. All right, so that is correlation. And correlation you can calculate on your calculator. One of the videos in one of your assignments in my labs has videos on how to calculate correlation. You just type it into your calculator, we'll see how it works in the regression, which we're about to look at. So linear regression, which is also sometimes called least squares regression, which we'll see why here in just a minute, is to two variables what the mean is to one variable. So the mean is a one-number summary of a set of data. And so the linear regression, it's an equation that kind of does the same thing, but for two variables. So for two variables, you can't just have one number. You've got to be able to display the relationship between the two variables, and we need an equation for that. So in statistics, linear regression is often used to predict outcomes. The x-axis values are our predictor variables, also in statistics known as independent variables, and then y is the predicted variable, also known as the dependent variable. Before we look at an example, let's look at a graph to see why it's called least squares regression. So this is a graph or a scatter plot of 5 data points. And what we want to do is we want to find the line that fits these best. So if I click here, all right. So this is an example of a line, but is this the line that fits those points best? In other words, if we had to draw a line that was the best estimation of these points right here, what line would it be? And so this little program here, we can adjust the y-intercept, we can adjust the slope if we want to, and so I'm going to try to get it kind of close. We're just trying to find something that predicts or fits the points the best. So the reason why it's called least squares regression is because we are literally trying to find the line that gives us the least or smallest squares. And we can actually see that right here. So those are the squares. The square is the distance from each point to the line, so that vertical distance, and then it's just squared. So that's what gives us the actual square. And so each of these, there's the square for that point, here's the square for this point, so forth and so on. So we want to make those as small as possible. So if I put my line, way up here, the sum of squares, the sum of all of these squares is huge. But if I move it down, they can kind of get smaller and smaller. And so we're trying to find this balancing point where the sum of the area of each of those squares is the smallest. And so if I click here, it'll show me what the actual line is. All right, I wasn't too close. But that line right there would give us the smallest squares possible. So let's see what that would look like if I try to meet that. So that's fairly close. It's hard to get exact. But anyway, that would be the smallest sum of squares. And so let's remove those. That is the best estimation of those points. So anyway, the calculator is going to be able to do that for us. It's going to be able to find that line for us. But that just kind of shows you the math behind what goes into finding that line. So we're trying to minimize the sum of the squares of the distances from the points to the line. All right, so now let's look at an example. All right, so in our example, we have the years 2009 through 2018. And we have the enrollment of new freshmen at the University of Arkansas. So in 2009, there were 2,919 new freshmen. And in 2018, there were 5,005 new freshmen. So what we're going to do is we are going to find the least squares regression line that gives us the best relationship between these two things, so time and enrollment. All right. So there's a note here that says, let X be the number of years since 2000. And this is really important, and I want you to write this down. Hopefully you're taking notes. But even if you're not, write this down. Know what X is. This is the biggest mistake that people make. So put stars by it, put a box around it, make sure on every single question that you do with linear regression, you know what your X values are. So it'll always say, let X be something. In this case, it says, let X be the number of years since 2000. It could say, let X be the year, or it could have said, let X be the number of years since 1990. Whatever it is, that's going to determine how we find our X values, and that's going to be really important. All right, so if X is the number of years since 2000, we could take 2009. How many years is that since 2000? Well, that's 9 years since 2000. 2010, that's 10 years since 2000. 2011, that's 11 years since 2000. And so we'll just go through all of those, and we could write all of those down. So each of these, they're pretty easy since it's the number of years since 2000. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 for the years 2009 through 2018. All right, so those are our X values. Our enrollment values will be our Y values. So in our calculator, we are going to put these in. So we're going to press the Stat button and then Edit. And then we are going to enter these. We're going to enter the X's into L1 and then the Y's into L2. So we got 9, 10, 11, 12. All right, I won't make you watch me type all of these in. We'll just fill all those blanks in. All right, so now we have our L1 and L2 list complete. And now we can find our regression. Before we do that, what we're going to do, we're going to press second and then the number 0 for catalog. And then we're going to turn diagnostic on. So we can, as kind of a shortcut, we can hit the D button right there. And then go down to diagnostic on. Diagnostic on. All right, so we're going to hit enter and then enter one more time. All right, so diagnostic is on. Once you've done this once on your calculator, you don't have to do it again. But what this is going to do is now when we run our regression, it's going to give us our correlation as well. All right, so we're going to hit the Stat button. We're going to go right one to Calc, and then we're going to go down to linear regression, linreg. It's the fourth option down. All right, so default, X list is L1, Y list is L2. If you have an older calculator, you're going to have to type those in. The way you'll type it in is you'll press second and the number 1 for L1, and then you'll type a comma, which is right above the 7 key, and then you'll press second and then L2 for L2. All right, so we're just going to go down and hit calculate. All right, and we see that our equation, y equals ax plus b, a, our slope, 190.38788788, and then our b, 1,890.96, and then it gives us our r value as well, 0.8685. So if we were asked for our correlation here, we could jot that down. All right, so our equation, 190 let's call that 39. So y equals 190.39x plus 1890.96. All right, so the questions in the homework will all tell you how many decimal places to round to. Since this isn't a homework problem, I just chose 2, but do be sure to check that in your homework questions every time you work one of these problems. All right, so in this problem, the actual enrollment is Y, but in the equation, this is the predicted enrollment. So it's a little confusing because Y can mean 2 different things. So the actual enrollment values are the Y values, but in the equation itself, Y is the predicted enrollment based on our regression line. So there's a homework question that asks what that Y value means, and it is the predicted enrollment in when the Y is in the equation. All right. Now let's use this to answer a couple of questions. So let's select this. There we go. And we'll put it here on our next page. All right. So we're going to answer a couple questions. First, in what year will enrollment reach 6,000? And then our second question is, what was the enrollment in 2005? And so both of these, we're going to try to find our values based on our regression equation. All right, so in what year will enrollment reach 6,000? So this is a predicted enrollment, right? So our x value is number of years since 2000. Y is the predicted enrollment. So we're wanting to know in what year, that's going to be our x value, will enrollment reach 6,000? That's our predicted enrollment. So to solve this, we're going to plug 6,000 in for y. So 6,000 equals 190.39x plus 1,890.96. And then we're going to solve. So we will start off by subtracting 1,890.96 from both sides. That's going to give us 4,109.04 equals 190.39x. And then we'll divide both sides by 190.39. And that is going to give us an x value of about 22. So remember that x is the number of years since 2000. So if our x value is 22, that's 22 years since 2000. So that would be the year 2022. So we predict the enrollment would reach 6,000 in the year 2022. All right, our second question is, what was the enrollment in 2005? Just as a note, the actual enrollment that year was 2,752. That's not going to be relevant to how we solve this problem, but we can look to see how close our predicted value is. All right, so we're predicting enrollment in 2005. We're kind of going backwards. So we want to know the enrollment, so that's our y value, in the year 2005. That's going to tell us our x value. So we have y equals 190.39 times x. So x is the number of years since 2000. That's 5 years since 2000, plus 1,890.96. And so if we solve for y there, if we multiply 190.39 times 5 plus 1,890.96, we get 2,843. Oops. 2,843, which is not terribly far from the actual enrollment, but is a little off. But anyway, our regression line is not perfect, but that is our predicted enrollment for 2005. All right, so that's how we can find a regression line and how we can find correlation. One of the other things that you'll be asked to do in the homework, and there's an example of this in the video, but I'll remind you here as well, is that sometimes you'll be given two regression equations, and you'll be asked where they meet, where they're equal. And as a reminder, a regression equation is just a linear equation, and two regression equations is a system of equations. And we've looked at a couple different ways in this class so far at how to solve systems of equations. So you can use any of those methods to solve where two regression lines intersect. So, all right, that's it for today. I'll see you next time.